Bismillahir Rahmanir Rahim. Assalamu alaikum and welcome to this session. In this session, we're going to continue our discussion on Markov chains, and we're going to focus on discrete time Markov chains. We're going to describe how they may be used, and we're also going to discuss what is the concept of a solution of a Markov chain. In the last session, we introduced the concept of stochastic processes, which is basically a mathematical tool with which we can analyze a process, an empirical process that is evolving in time in a random manner. And using stochastic process, we make use of a family of indexed random variables with a single random variable dedicated for an observation, a point, and then they have some relationship and dependence amongst each other. And we classified stochastic processes according to whether the observation index is continuous or discrete, whether the value it can take is continuous and discrete, continuous or discrete, and lastly, what is the nature of dependence between the random variables. We were especially interested in the dependence in which the future state is dependent only on the current state. And we called this the memoryless property, in which process does not have to memorize all of its history. The next step is only a function of the current state. So now we are going to see this again, the Markov memoryless property, and we can see that for the next instant, the random variable for that, for xn plus 1, the probability of that taking a value of j, given all the history, is just the same as probability of x n plus 1 is equal to j, given the current state is a value I. So we can in fact express this in the form of Pij, which is a shorthand of expressing what is the probability of going to j, given that you are in the ith state currently. In the last session, we discussed that amongst all Markov processes, we are interested in Markov chains, in which our process can be in some state of a countable set. This countable set may be finite or it may be infinite, but in the context of network performance evaluation, we are always going to focus, especially in this course, on the processes in which the process can take a discrete value, or the state is a discrete value. So we call such processes Markov chains, and our focus is going to be on discrete time Markov chains, in which we are going to observe this Markov chain at some deterministic times. Typically these times are fixed. They may be regular or they may be irregular, but the key idea is that we already know when the next observation would be. So with this background, let me now introduce to you the outline of this session. Initially, I'm going to motivate the idea of a discrete time Markov chain with a simple example, in which we are going to model temporal process that is random. That is, it is a process that varies with time, and we do not really know, given the current state and the history, in a deterministic fashion what the future state would be. And then using tools of discrete time Markov chain, we are going to see what information can we gather about the empirical process. Secondly, I want to talk about state properties of discrete time Markov chains. There is a kind of a discrete time Markov chain which is very appealing to engineers because it lends itself to very useful properties. If we have a chain that belongs to this class, which is known as an ergodic class, then we can talk about this chain in the long run, and we can say what would be the average probability of being in different states. And these probabilities are not going to be a function of the initial state. So this is very useful. If you have a process which can be represented by an ergodic Markov chain, you can talk of the question that given any arbitrary random time in the some random snapshot of the process, what is the probability that you would observe the process in this state, in the other state, in the other states? And you can answer this question for all the states of your Markov chain. After developing these properties, and we'll be discussing what are the desirable properties, the properties that we want to work with, and also conversely we'll be highlighting what are the properties that we do not want in our Markov chains. Because if our Markov chain has those properties, then it becomes too messy and we are not able to analyze this and give a steady state solution. And lastly, I'm going to talk about solution of a discrete time Markov chain, in which we talk about both the transient analysis, in which we may ask that, okay, this is our model, where will we be after so many steps? This is known as transient analysis, and using such analysis we can estimate how the process or the chain is going to evolve in a short time. But if we are interested in the asymptotic case or the steady state case, we make use of the limiting distributions. So we're going to talk about all of this. Initially, I start with a motivating example. So you may know that weather is notoriously very hard to model, because we cannot know for certain how the weather would be like in, let's say, 1 month from now. We can only talk in probabilistic terms, depending on the history of the place you are, depending on the time of the year and so on. But we cannot know in a deterministic fashion how this weather process is going to evolve. So for the sake of simplicity and for the purpose of motivating the need of discrete time Markov chains, I'm going to construct a very simple model of weather, in which we classify the weather into just 2 states. One state is the state in which we do not have any rain, and we call this state as a sunny day. Regardless of the fact if the sun is out or not, we would call this a sunny day. In contrast, you have a rainy day, and we want to see every observation. We're going to look out of our window in the morning and see if it is actually rainy or not, and accordingly we're going to make observations. So the idea is, if we represent this by a discrete time Markov chain, this is a discrete time chain because our observations are fixed in time. We know beforehand when our next observation would be. It's a Markov chain because it can only adopt from a set of values that are countable. So how do we actually construct a model, a probabilistic model, that tracks what our expectation is for different observations? So if you see on the slide, you would see that the main idea we are trying to convey here is that you have a dynamic system, in which a dynamic system is basically a system that varies with time. And not only is our system dynamic, but it is a probabilistically dynamic system in which the future state is not deterministic. So we can model this with a combination of 2 things. The first thing is going to tell us what are the possible states our process can be in. So we've just mentioned, for the sake of simplicity, we're going to just abstract away everything and just consider 2 states, sunny and rainy. The other thing which is important is that what are the transition probabilities? And if you recall, in a Markov chain, the next state is only a function of the current state. So in fact, this transition probability matrix is a complete characterization of the discrete time Markov chain along with the state space. We do not need to know all of our past history. Just these 2 things are enough to characterize and model this dynamic system in the amount of detail that we have specified. One thing that you must note is that this memorylessness property is a function of our model. So it is not really the case that the weather is memoryless. In fact, the weather typically is not only a function of the current day, but it also is a complex system in which the weather of the past many few days affects the future day's weather. But we have constructed a model and for that model, memorylessness is a property. So we must not confuse the abstraction that we're using for a process and the process itself. Okay, so if we have this model, how can we analyze this, and what are the interesting questions we can ask? So we can ask our question that, okay, given that today is a sunny day, what will be the probability of the next day being sunny, the next day being rainy? And in fact, this very information is needed as part of the specification of the model. This is part of the transition probability matrix, which defines the probability of a future state contingent on being in some state. If we advance this idea further, we can talk in terms of n-step transition probability. Given that today is a sunny day, what is the probability that the third day would also be a sunny day? The fourth day would also be a sunny day. And if we extend this concept, and we may even extend this idea to what is the probability of any random day being chosen being a sunny day. And we are actually interested in precisely this question, because once our knowledge of the process has come into a steady state, the probabilities are going to become stationary, and then we can talk in terms of steady state probabilities. And this is one very important concept, that the state that you start a particular process in has an effect on the future states, but typically it would die down and eventually the Markov chain would mix, so that you have a consistent expectation of what would be the weather 10 days from now and 11 days from now, especially if this is a stationary probability. When we get to a stationary steady probability, this expectation does not change. So in fact, we are going to build on these concepts, use more concrete examples. So let's now just focus back again on the preliminaries. Having seen the probability matrix, let's now provide some values for this probability matrix. Let's say if the current day is sunny, the probability of the next day being sunny is 90%. So that would be 0.9 probability. If the current day is rainy, the probability of the next day being rainy as well is 0.5. So we express this in the form of a P matrix, and if you observe, this is a stochastic matrix. The sum of all rows is equal to 1. This is because these are representing probabilities. You're going to make a transition to some state, because in a discrete time Markov chain, every observation, a transition has to be made, even if it is back to the same state. In fact, in this matrix, the P matrix, 0.9 is the probability of being in the sunny state and making the transition back to the sunny state. And from this, we can infer the probability of being currently in the sunny day and the next day being a rainy day, which would simply be 1 minus 0.9 is equal to 0.1. And if we sum both of these up, 0.9 plus 0.1, it would be equal to 1. It might be apparent to you that the actual weather system is a lot more complex than our model. And if that is a real concern to you, for the particular task that you're modeling for, remember, models are made specific to the task they are trying to solve. Accordingly, if capturing the weather in more finer detail is important to you, what can be done is that we may consider more history while deciding the future state after the transition. And typically that makes our model more complex. As an example, let's say the weather tomorrow is not only a function of the weather today, but also the weather yesterday. And together this decides where we will be going next. So to keep the Markov property intact, we would actually have to create more states. And instead of 2 states, as is the case now, you would have 4 states. So the first state would be that the previous day was a sunny day, the current day is a sunny day. This is the first state, We call this the SS state. Accordingly, for all the 4 combinations, you would be having particular states. And then the transition is made based on the Markov property. I hope it is clear to you that using this hack, we are actually able to incorporate some history as well. And also, we have the Markov property, which makes things easy for us to calculate. And generally speaking, we can extend this concept to include more history, but it must be remembered that in an engineering and scientific task, it is usually preferable to have the simplest model that you can have, which explains and is good enough for you. Having a more complex model introduces many difficulties. Okay, now let's proceed further and talk about, in more precise terms, what is a state probability that we want to solve for. I've stated earlier that given a discrete time Markov chain, we want to know the steady state probability distribution. That effectively answers the question that, okay, if we take a random snapshot of the future and we look up the process to see where the process is, in this example, it would be any random day of the future, let's say the 75th day. We just look it up and we want to know the probability that it will be a sunny day and the probability that it would be a rainy day. If we can answer a question like this for our model, then this would be a steady state probability question. And in many chains, especially the well-behaved chains, the state probabilities actually converge. So that is particularly useful for us because then we can answer questions about the chain in asymptotic terms. Our initial starting point is soon forgotten and we get into a steady state where it does not matter in which state we started from, eventually everything is going to converge. For example, if our steady state probability eventually converges to 90% sunny days and 10% rainy days, so it does not matter where you start from. If the model that we have is an ergodic model, which we would see later on in this session, and it's a well-behaved model, irrespective of the starting point, your state probabilities would converge to this in a limiting sense. So let me define some notation now. We have an initial state probability, and that is represented by pi with 0 in the superscript. So that actually tells us that for all the possible states that you have, in the general case, you can have countably infinite states. But for all the states that you have, what is the probability that the first observation would be in any one of these states? So every state has an initial state probability. And with that, that is the starting point from which we get into this process. And then we are going to observe the random process and answer questions based on in probabilistic terms. But this is the notation, and everything that we would be defining next is actually following from this. In this case, we had pi and within brackets 0 in the superscript. In general, if we are answering a question about transient state probabilities, it would be a question like, after 5 transitions, where would process be? What is the state probability distribution for that? And to express that, we make use of a vector pi, and within brackets we have n. And n here tells us that this is the nth time in which we are making the observation. And then we can answer for every state, what is the probability that the process would be in these particular states. The limiting state probability matrix or the vector is the case in which you have infinity in the superscript. That effectively tells us that what are the state probabilities for each one of these states at a random snapshot, where the effect of the initial conditions have been forgotten. And that would especially be the case in ergodic chains, where the steady state is unique irrespective of where we started from. So let me introduce more definitions today, and please bear with me in this lecture and in the next continuous time Markov chains. we're going to see lots of definitions. And most of the definitions are important because we'd be using this theory when we get to the study of queuing theory. So if we are careful at this time, the things that are going to come next are going to become easy. Okay, so we've seen what state probability matrix is, and we've defined it to be pi, and this pi, the superscript associated with it, जो चीज ऊपर brackets में लिखी हुई है, that is telling us the time associated with this state probability matrix. But what we are actually interested in is that at any given time, irrespective of the starting point, what are the state probabilities? And that is the case of limiting state probability matrix, where the superscript is written as infinity, and in many cases it is omitted. So if you only have pi, this is a vector in which you have one pi for every state. So pi 0 is the probability that in the long run you'd be in state 0. Pi 1 is the probability that in the long run you'd be in state 1, and so on. An important kind of a probability matrix is a stationary state probability matrix. This is a matrix in which if we are in this state, after a transition, the next state probability is not going to change. And this is very useful because when we get into this state, you would keep on making transitions and your expectation of where you would be would remain consistent, or it would remain stationary. In the case of ergodic chains, which is really what we are after, we would see that in the limiting case, we would have a stationary state probability that is unique, and it actually is the same irrespective of the starting point. So this is very interesting actually. If you have an ergodic Markov chain, irrespective of the starting point, eventually it's all going to be the same, and we are going to see that today. Okay, so let me now talk about the solution of a discrete time Markov chain, and I'm going to come very soon back to the weather example, but let me now just try to reinforce the concept of a state probability matrix. Pi superscript 0 is the probability of being in different states initially. So for every state you would have some probability of being initialized in that state. Pi superscript 1 is equal to pi superscript 0 multiplied by the P matrix, which is the probability transition matrix. So using these matrix multiplication, we can find out the state probabilities after one transition. In a similar way, after we have this pi superscript 1, if we multiply this with P again, we would have pi superscript 2, which is the state probabilities at time is equal to 2. And this is a very general concept which we can extend, and if pi superscript infinity exists and the limit applies, then we would approach the steady state probability. After having studied these concepts, let's come back to our example so we can apply this knowledge there. Okay, let's say we want to study our example of weather in a transient way. We don't want the steady state analysis currently. We just want to know that, okay, we started from this. At time t is equal to 0, the weather is this. What is the chance that after one transition you'd be in some state? Either the sunny state or the rainy state. We want probabilities for that. So now I am showing the same probability matrix as well as the transition diagram. It's just shown a little differently so that you would come to realize that the depiction does not matter. The size of the nodes and of the vertices can be made large or small. It is actually the edges that are important. So these are all probabilities. If we see the arc going from vertex S to R, this is the probability of being in sunny state and the next state being rainy. So let's see, if we want to calculate the weather for day 2, how can we actually solve this? So to solve this, we need to know the initial weather condition. In the transient analysis, the initial conditions are very important, and they actually in many cases dictate where you will be in the short run. So assuming that the initial weather condition is sunny, that is, you're going to start in state 0 with probability 1. So every time this Markov chain will be initiated in the sunny case. If that is the case, weather probability on day 1 would be pi superscript 0 multiplied with the P matrix. This is the matrix multiplication. And we get values of 0.9 and 0.1. So these are state probabilities. The probability of being in state sunny is 0.9 and the probability of being in state rainy is 0.1. And this actually just follows from the P matrix. If you recall, that is exactly what is the probability of the next state dependent on the current state. We are interested in solving for day 2. That's simply this thing multiplied by another P. So this thing is multiplied by P and we get the values of 0.86 and 0.14. This is a very simple example, but it serves to illustrate how transient analysis works through. Okay, now my question to you is, would change in the initial conditions affect our expectation of weather on the second day? So if you think about this, you would come to realize that in fact it does matter. In the short term, it does matter. So if we, for example, started in a sunny day or a rainy day with equal probabilities, 0.5 and 0.5, then the probability of the second day being sunny is no longer 0.86. It's just 0.78. So the short-term probabilities are actually dependent on the initial conditions. But what if we actually want to calculate for the long run? And we would be really interested in the case where the effect of the initial state probabilities is not that large. So let's consider the case of steady state distribution, calculation of that. We start from the same place, be given P, and assuming that the initial weather is sunny with probability 1. So if we calculate for longer and longer number of transitions, for day 1 it would be 0.9 and 0.1. For day 2 it would be 0.86 and 0.14. On day 4 it is coming to be 0.837 and 0.163. For day 16, knowing that currently you started with a sunny day, the 16th day, the probabilities of that being sunny is 0.833 and the probability of that day being rainy is 0.167. So if you observe carefully, it seems that we are converging towards some numbers. And in fact, if we multiply P by itself, or otherwise we have the notation of P raised to 16, we actually get a matrix in which the rows are the same. And this is the trademark of a converged transition probability matrix. If you have a probability matrix like this in the long run, then you would have a limiting distribution that becomes stationary. So in this case, I repeat the question to you which I asked for the transient analysis, that would change in initial conditions affect our expectation of weather on the 16th day or any random day in the future. If you realize and if you observe this carefully, this is really profound. Irrespective of where you started from and any random day in the future, you want to know what are the steady state probabilities. And in fact, the answer to this question is a no. Any initial condition would give us the same weather because in the long run, the probabilities are going to become stationary in a limiting sense. And that is what we are really interested in. In many cases, we actually want to have the steady state distribution. The steady state distribution, if it exists, can be calculated by solving the system of linear equations. Pi is equal to pi multiplied by the matrix P. And we also know that the sum of being in some state is equal to 1 because these are probabilities. So I hope with this example, the motivation and the idea of Markov chains, the discrete time Markov chains, have become clear to you. Let's now talk about some state properties to actually discover what are the kinds of chains that are well behaved, which will actually give us steady state distributions that are the same irrespective of the starting points. In other words, irrespective and forgetting where you started from, you're eventually going to converge onto a unique steady state probability distribution. So accordingly, we're going to develop some ideas about different kinds of chains, and we're going to call some of these chains pathological, which actually tells us that these are bad chains, these are bad properties. We do not want that, because if our chains have those properties, things become messy, and the steady state probabilities do not exist. So because of that, we exclude many kinds of chains, and we focus on a particular kind of chain, which you would come to see is known as a ergodic chain. But let's start from some basic definitions. Let's talk of a recurrent state. Initially, I'm going to talk about properties of states. So a chain itself is composed of multiple states. अभी हम properties discuss करेंगे states की. A recurrent state is a state to which we are certain of returning. So if you have a state and you make a transition out of this, if a question is asked that what is the probability that eventually you'll come back to this state, if that probability is 1, then this is a recurrent state. यानी बार बार आप वापस आएंगे. If the probability is less than 1, then you have a transient state, and we don't want transient states, because if you have a transient state, it may be that you make a transition and you never come back, even in the asymptotic case. So then the steady state probability would be 0. We don't want that. We want to have recurrent states. Even in recurrent states, we have two different kinds of recurrence. And these are important when you have the concept of a countably infinite discrete time Markov chain. So in such a chain, the number of states are infinite, but they may be counted. So a funny situation arises in such cases where you do have recurrence, and it is certain that you would come back, but the mean time that is expected to come back is infinity. So that is not a useful kind of recurrence. We call such recurrence null. We don't want that. We want recurrence non-null, also known as positive recurrent. So we want all of our states to be positive recurrent. Fortunately, when we consider finite state Markov chain, this problem does not arise, especially if we're considering irreducible chains, which we're going to cover very soon. Okay, let's now talk about periodic states. Periodic state is a state in which there is a natural period of coming back to. So for example, if a state goes out and it can only come back at either the second transition or the fourth transition or the sixth transition, and not at any other transition that is not divisible by 2, for example, it cannot come back at 3, then we call this a periodic chain. If we have a chain in which you do not have such a period larger than 1, we define it to be, I would say that a recurrent state is periodic if return to this state is not possible except as a multiple of some integer multiple of d greater than 1. If the greatest integer that you have of the period defining your returning back is some integer multiple of 1, that is not a problem. So that is in fact the case of aperiodic. You can come back at any number of transitions. We actually want aperiodic states. Periodic states are not good for us because the initialization has a long effect. If you have a periodic state, then depending on where you started from and the current phase of your period, the state probabilities are going to change, and therefore they would never become stationary in a limiting sense. So for all of these properties, let me tell you what are the desirable properties that we want. We want recurrent states that are positively recurrent. So you come back to the same state again and again with probability 1 in finite time. Also, we don't want transient states. We want states that are aperiodic, because having periodicities affects the concept of steady state probabilities. Okay, let's now talk about ergodicity, the thing that we are trying to develop all these states for. Ergodicity is defined as positive recurrent aperiodic states if we have all of these together, and if we have the concept of irreducibility of the chain, which we will see very soon when we talk of properties of the chain, then your overall chain is ergodic. But currently we are only focusing on the states. Therefore, a state is ergodic if it is positive recurrent, if it is aperiodic. We call this state ergodic. In other words, return in finite time is certain without any periodic restrictions. And that is, I just said, this is what we want, and what we want is ergodicity. If we give a name to what we want, we would say that we want ergodicity. There is another property which is interesting for our study, and that is you may have a state that is trapping. That is, if you get into that state, you cannot get out of it. This is also known as an absorbing state. We do not want such a state in our chain, because if you get there, you will never return to the other states, and therefore the recurrence would be affected. So now we are in a position to talk about the properties of chains. A chain may actually have multiple classes. So a chain has multiple states in which some states can only talk to each other. And the concept of communicating states class is that both of them can speak to each other. Not necessarily in one transition, but they can reach each other in multiple transition possibly. But reachability is assured from both directions. Okay, now talking about properties of chains, we have a property of irreducibility. And that is that a chain has only a single communicating class. In other words, आपकी चेन के अंदर जितने भी states हैं वो सब एक दूसरे को reach कर सकते हैं. It is not the case that you're going to reach in some state and never go back. If you have such a case, we have the problem of reducibility, जिसमें आप in some cases even reduce the chain into different parts. But if you have an irreducible chain, every state of that class is able to talk to each other, and in an irreducible chain, we only have a single communicating class. The homogeneity of a chain is the fact that the transition probability matrix is not a function of time. So irrespective of time, you're always going to have the same P matrix. The probability of making the transitions, the one-step transitions, they are going to be invariant to time. And lastly, the concept of an ergodic chain. We've discussed ergodic states. The concept and the extension to chains is very simple. If all of your states in a chain are ergodic, then you have an ergodic chain. In other words, it consists only of ergodic states. That means they are positively recurrent, they are aperiodic, they are homogeneous, and therefore the thing that is most relevant to us is that if you have an ergodic chain, you would have a unique limiting state probability. That is what we are after. Okay, let me now discuss all of these pathological conditions just one more time so that it becomes very, very clear to you what we don't want. Ergodic discrete time Markov chains exclude some properties. For example, non-homogeneity is excluded, because if you have a non-homogeneous chain, then everything is a function of time, and then you're not going to converge into a steady state distribution. Reducibility is another thing we don't want, because if you have reducible chains, then depending on the initial conditions, it may be that you will never reach some states, and we don't want that. In a steady state distribution, every state has a non-zero probability of being reached, and these are the kinds of chains that we are actually interested in analyzing. If you have a reducible chain, the effect of initial condition is permanent. If you have periodicity, the phase in which you currently are in is going to affect the state probabilities. So this is another pathology. Lastly, we don't want transients or even null recurrence, that you are returning but after a very long time. So all these four properties are excluded, and if you have that, you have an ergodic Markov chain, which are very simple to analyze and have good limiting properties in the sense that they have a steady state distribution. Okay, let me now talk about the solution of a discrete time Markov chain, and we can talk in terms of a transient solution and also a steady state solution. We're going to start with some theorems which are actually going to tell us some interesting things about how different Markov chains work. The first theorem is that if you have an irreducible Markov chain, then the properties of all the states of this irreducible chain are going to be the same. Because if you have an irreducible chain, then all the states are in a single class. The interesting thing is, then all of them have the same properties. If they are transient, then all of them are transient. If they are recurrent, then all of them are recurrent. If they are recurrent null, then that is the case for all the states in that particular class. Also, if you have a property of periodicity, then all the states belonging to that class would have this property. So there are some interesting lemmas that follow from this, and we can see that from the slide. The first one is that if you have a finite irreducible Markov chain, then all states are recurrent. This is a very interesting property, and finiteness gives this to us, because irreducibility tells us that you're going to come back, and because we have finite states, then the problem of recurrent null does not arise. That is only a problem when you have countably infinite large states, and in that kind of a chain you may have recurrence that is null, which means the average expected time is infinity. You would reach back, but it is going to serve no purpose because the time is going to be very large. But if we have finite Markov chains, this may states finite. In that case, you would always have recurrent states inside a single class. All these states are recurrent. The second lemma is that if states of a countably infinite irreducible chain are transient or recurrent null, then pi j is equal to 0 for all j and no stationary distribution exists. So accordingly, if we have a Markov chain having countably infinite states, even then we want recurrence that is positive. We don't want transient states, and we don't want recurrent null states. And in fact, we have an example in which we show if that is the case, steady state distribution is not defined. Let's talk of another theorem which states that in an irreducible and aperiodic homogeneous Markov chain, the limiting probabilities always exist and are independent of initial state probability distribution. So this is very useful for us because this is exactly what we need. We want limiting probabilities that are independent of initial state probability distribution. And when do we have it? When your chain is irreducible, it is aperiodic and homogeneous. Furthermore, if all the states are ergodic, which means that they are recurrent non-null as well, in addition to the property of irreducibility, aperiodicity, and homogeneity, then pi j is greater than 0 for all j, and it can be uniquely determined by just solving some simple equations, and those are that pi j is the sum over all states is equal to 1. So you're going to be in some state, and the other one is going to be developed in the future slides just very shortly. So let me show you an example in which we can just by inspection see if our steady state solution would work for this or not. We have two chains here. The first question I ask is that are these chains irreducible? So for that you need to see if it is possible for all states to reach all other states. And if you work this out, you would see that they are in fact irreducible. They can reach each other. The other point is, are they recurrent? So it is obvious from the theorem on the previous slide that this is finite Markov chain and these are irreducible. They all belong to a single class. Accordingly, all these states are recurrent, and that would be the case when you have a finite irreducible Markov chain. So up till now we are fine. The third question is any one of these chains aperiodic? And now we can make out that the left hand side chain is fine, but the right hand side is periodic, because you can only reach one state after making a transition. You can only come back in periodic terms, and that period is 3. So you can only come in integer multiples of 3, and that is bad for us because then we cannot use the concept of steady state probabilities. And lastly, the question, are these chains ergodic? Because the right hand side chain is not aperiodic, therefore it is also not ergodic. The left hand chain is ergodic, and usually if we have a self loop, like in the left hand side chain we have a self loop from 3 back to 3, then we should be fine, because then that breaks down the periodicity. Okay, solving a discrete time Markov chain is usually done through balanced equations, because the idea is that in equilibrium you are going to be in a state where the steady state probabilities are not going to change at every transition. So pi is equal to pi multiplied by p, and if written down in the matrix form, we would have what is shown in the slide. So we have to solve for this, and the other thing that we have given is that the sum of all over all j of pi j is equal to be 1. And given this, we can actually come up with a solution. The general intuition is that the long-term transitions out of a state I is going to be the transitions back into state I if the state probability is going to remain constant. And that is what happens if we have stationary probabilities. So let's consider an example. In this chain, we have 3 states, and this is an ergodic chain. So as an exercise, please try this out if this is actually ergodic, and you would see that this is. To actually get the solution for this, we make use of the fact that pi j sum over all j is equal to 1, and pi is equal to pi p. In other words, the matrix multiplication of pi and p is going to give us pi again. And if we do that, we come up with 4 equations in addition to the summation of pi j over j is equal to 1. And you can solve that to get results for the short term and also for the long term. In the long term, we know that we're going to be in an equilibrium where the transitions into the state and out of the state are going to be the same. The last thing I want to cover in this session is the case in which you have a discrete time Markov chain in which you have countably infinite states. Our question is, does a steady state distribution exist for this discrete time Markov chain? And now, because we are dealing with infinite states, things become a little hard. It's not very straightforward if a steady state distribution exists or not. And in fact, that is dependent on the values of p. So if p is something, then it may have an effect in which every state becomes transient and you keep on growing. And because of that, you're never going to come back to a state, and therefore steady state probabilities do not exist. So let me show you how that works. Steady state distribution can be found as the multiplication of pi and p and equating that with pi, and we know that the sum of pi I over all I is equal to 1, and the general formula that we have can be seen for some random pi j, which is the steady state distribution for state j, and also we can find out for the 0th state. You can observe that the jth state probability is actually a function of the 0th state probability. So now we can state some results. We see that for the process, the Markov chain shown, if p is less than 1 by 2, then all states are transient, because now the probability of coming back is less than half, and you're going to keep on going ahead and ahead, and eventually you're never going to come back to a state. And because all the states become transient, since this is an irreducible chain, the properties are going to be shared. If you have p more than 1 by 2, then you have positive recurrence, and in such a case you can have a steady state solution. If you have p is equal to 1 by 2, you have all states null recurrent. This example is important because it has applications in queuing theory. If you have a queue and the service rate is less than the arrival rate, then things are going to just pile up. If you consider the queue, then the size of the queue would keep on increasing. So in this case, you will never come back to the state where there is no one in the queue, and that would be an unstable system. Okay, let me now recap everything that we've covered in this session and conclude this session. I've stated that a discrete type Markov chain can be used to model a process evolving in time, that is, random process can be modeled, and we specify a discrete time Markov chain by its state space and also the probability transition matrix. For ergodic chains, we can calculate the steady state distributions, and we can use either the notion of the probability transition matrix raised to a very high number, p raised to n, where n tends to infinity, and then all the rows become equivalent, and that actually tells you the state probability distribution. And we can also solve for the balance equations, as we saw at the end of this session. The steady state distributions are very important because based on that we can then find out performance measures. So we're going to continue discussion about Markov chains, and in the next session we're going to talk about continuous time Markov chains. So till then, assalamu alaikum wa rahmatullah.